Hello fellow problem solvers! So today we're going to be doing a good introductory combinatorics problem from the German Federal Math Olympiad 2002 first round problem 1. I suggest you try this problem out for a minimum of 5 minutes, ideally 20 to 40 minutes, but not more than 1 hour. If on the other hand you'd like to go along with us, I suggest you take 5 minutes and figure out what would your approach be. How would you solve this type of problem? So now, let's begin. So in this problem, we have this planet Ypsilon with 365 days, just like our planet, and each month has either 28, 30, or 31 days, and we need to prove that there are 12 months in a year on this planet. Now, one of the things when you start solving these types of problems is how do you turn these words into something that you can actually work with and prove and have claims about. So one way to do this here is to say, okay, let's say this planet has X months, which are 28 days, Y months, which are 30 days, and Z months, which are 31 days. And then the whole year has X times 28 plus Y times 30 plus Z times 31 days. And what we need to prove here is that X plus Y plus Z is equal to what? 12 months, because this is how many months are of the length 28, how many months have 30 days in them, and how many have 31. And we need to prove that X plus Y plus Z is equal to 12, where this is equal to 365. Now, if you haven't figured out this sort of algebraic representation before this, I invite you to take another 10 to 20 minutes and see if you can work with this. If you can go from here, X times 28 plus Y times 30 plus Z times 31 is 365, where X, Y, and Z are non-negative integers, can you go from there to proving that X plus Y plus Z must be equal to 12? Take those 10 to 20 minutes now. One approach here is that you actually try to find what X, Y, and Z are, and a way that you would do this is you would say, okay, let me do some maybe modular arithmetic, maybe look at, okay, the last digit needs to be 5. So I need to have, okay, the relationship between the Z's and the X's is some specific relationship. If I have Z, like what is this whole, we need to have Z plus, actually minus 2x needs to be congruent to 5 modulo 10, because 28 is minus 2 and 31 is 1. This is 0, so this must be congruent to minus 2 modulo 10. And now from here you could perhaps even enumerate the possibilities for Z and X. The trouble is here that, once you pick a Z and an X, you're sort of forced on what you get a Y. Now, trouble with this is, it's not that big of a trouble. You can still work with this. Say if X is congruent, if there's 0 X's, then Z is congruent to 5 mod 10. Now, does that mean Z is 5 or 15 or what? Or 25? Well, obviously it can't be 25 because 25 times 31 will be way past 365, and then Y might need to be negative in that case. So there is something about the size of all of these. Now, that's one way of thinking about this. Another way of thinking about this is, instead of trying to actually solve this thing for X, Y, and Z, another way of thinking about it is, you need to prove X plus Y plus Z is 12. What if it's, say, 15? What do you have then? Take 10 and 20 to 20 minutes and try to figure out what happens if X plus Y plus Z is 15. Well, you can see that no matter how you put X, Y, and Z where they're positive integers, if their sum is 15, this whole thing is going to be greater than 365. And now here's a way you can actually prove that. Say that X plus Y plus Z is equal to 15. Then we know that 365 is equal to 28x plus 30y plus 31z. And now this thing right here is greater than greater than or equal to actually 28x plus 28y plus 28z. Why did I do this? So I can have x plus y plus z in a parentheses like this. Multiply. Now I can use the fact that this is 15. And what do I get? I get this is 28 times 15, which is equal to 280 plus 140, which is 420, which is much bigger than 365. And now if this is greater than or equal to 15, well then here, this is not going to be equal to this, but rather is going to be greater than or equal to 420, which is again a contradiction. I invite you to now maybe use this and also think about the other side. What if x plus y plus z is 10? What do you get then? What is a problem that you run into then? Or 11? And the way to do this is, say, we do case 1. Say x plus y plus z is less than or equal to 11. What does that imply? This implies that 365, which is equal to 31z plus 30y plus 28x. Now it's less than or equal to 31z plus 31y plus 31x. We want less than or equal to get a contradiction and to be able to use this. And now this is 31 times z plus x plus y. And now this is less than or equal to 31 times 11, which is 341. But this right here is a contradiction. So that means x plus y plus z can't be less than or equal to 11. And now we move on to the second case, namely, x plus y plus z is greater than or equal to 14. And the reason I'm doing 14 instead of 13 is because with 13, we don't quite get a contradiction. But with 14, what we're left with is 365 is equal to 28x plus 28 plus 30y plus 31z, which is greater than or equal to 28 times x plus y plus z, which is greater than or equal to 28 times 14, which here is equal to what? It's 280 times plus 4 times 30 minus 2, which is equal to 400 minus 8, which is 392. And this right here is a contradiction because this isn't greater than or equal to this. So now we move on to the third case, namely x plus y plus z is equal to 13. And now what do we do with this case? We don't quite have a contradiction because 28 times 13 is 364. So now what's the best way to deal with this? I invite you here to take about, let's say 10 to 20 minutes and try to figure out how would you solve this case. And here's a way I would think of as elegant. I'll just substitute x is 13 minus y minus z into here. And now what do I get? I get 28 times 13. And now it's going to be 28 times minus y plus 30y, which is going to be plus 2y plus 3z is going to be equal to 365. Now what is this right here? Well, this right here is equal to 364 plus 2y plus 3z is 365, where y and z are non-negative, positive, non-negative integers. And now this implies that 2y plus 3z must be equal to 1 for some y and z, which are non-negative positive integers. And now we can say this solution does not have solutions in the non-negative integers, because if y or z are greater than or equal to 1, then the whole expression is greater than or equal to 2. If they're both 0, then this is 0, so this is never 1. And this equation does not have a solution. So this case doesn't give us a solution, which means that the only possibility left, 13's out, greater than or equal to 14's out, less than or equal to 11 is out. And now this implies, so cases 1, 2, and 3 imply that x plus y plus z must be equal to 12. And now we are done with the problem. And as always, thanks for problem solving.